And just to make sure, one more time, just to make sure, when I minimize this, there it is. All right. We're in good shape. No names there. All right. Thank you very much. Hi, guys. How's it going? You guys look bright and chipper for 8 o'clock in the morning. I got to warn you, I've had about a pot of coffee, and I'm really wired, so this will be an interesting lecture. First of all, I want to remind you, I know the grades have not been posted yet. That should happen any time. I do want to remind you the musculoskeletal block evaluations are open. Don't forget to fill one out. If it can help us to change something, or if you want us to change something and you want it to happen, the evaluations are where we need to see it. The Thursday lunches are great, but it's still just a dozen students in the room, and so there's always this, well, that's just 1 or 2 students. If it comes up on the evaluations, it comes up maybe 20 times or something like that, something will get done. It doesn't necessarily mean that we're going to do what you suggest, but perhaps we'll make a better effort to explain what we're doing or something if it comes down to that. These evaluations do go through at least 2 committees, and they do land on the dean's desk, and we do take them very seriously. I would encourage you to be specific when you have suggestions to make. I would encourage you to be constructive, and I would encourage you to name names. It does not help me if you make a comment about workshops, for instance, in physiology, unless you name the person you had, because the sessions tend to run differently, and we don't know exactly what you're referring to or who you're referring to unless you name names. We will not take offense. We need to know. Related to that, I have the Thursday lunch down here. I haven't put that list together yet for next week, but I do want to mention that the students, the one comment came across loud and clear about the last block, and that was about the practice exam. We ordinarily, when students walk up to me and say the practice exam was easier than the real exam, I go, well, people have been telling me that for 14 years. Because the practice exam, you have the book open in front of you, it usually seems easier. Last block, we recognized that that was not the case, that the practice exam was easier, that there were not enough application questions on it, and we are solving that issue this block. So I want to assure you that this practice exam will better reflect what you'll see on the real exam. Doesn't help you with last block, but that comment came through loud and clear. We agree with it. We totally agree, and we will solve that problem, okay? To remind you, the Human Cardiac Cycle Lab starts today. I am psyched. I love this lab. I think you guys are going to like it too. Okay? Make sure, if it's not too late yet, to identify a conflict on the schedule. All of a sudden you realize you've got anatomy at the same time, because I blew it when I put the schedule together. If I did, let me know. We'll just put you in another group on another day. Okay? Don't forget the membrane self-study. That needs to be done before Tuesday next week. That is when my action potential lecture is. Again, you don't need to do it if you feel like you're really up to speed on the skeletal muscle and nerve action potential stuff. If you feel like you struggled on that on the last exam, you better review it, because I have to assume that you're going to know what I'm talking about when I refer back to that lecture, because I don't have time to go over it again. Those lectures used to be back to back to back. I used to do membrane transport, resting potential, skeletal muscle and nerve action potential, synapses, and then cardiac action potential all in a row. That does not happen anymore. Once the block system kicked in, Dr. Levin won't let me do cardiac action potential in the musculoskeletal block. It's a cardiac issue. He wants it done in cardiac. I understand that. But it does separate those lectures a bit, so make sure you're up to speed on it. It is not a particularly easy lecture. Lots and lots of channels, lots of things to digest, but fortunately, repetition is the mother of learning. We have workshops. We have other things related to it. You'll get it. Cardiovascular self-study and hemodynamics before 11 and 11. That is when the hemodynamics workshop is. And I am going to assume that you read that and have comprehended it. It is relatively straightforward material. Much of the stuff in the cardiovascular self-study, the structure and function of the cardiovascular system, we'll be going over again. Repetition is the mother of learning. But if you expose yourself to it by reading through it first, that will help you a great deal. Okay. So let's start out with our dilated cardiomyopathy case. Okay? She has a soft holosystolic murmur. Of the three choices below, this murmur is most likely to be caused by what? Let's start with number 3. Okay, first of all, let's think about this for a minute. Okay? We're hearing a murmur at some point, and it's going to be at some point in the cardiac cycle. Okay? And depending upon where you hear it relative to the first heart sound, which is when the AV valve is closed, the tricuspid and the mitral, and in relation to the second heart sound, when the semilunar valve is closed, the aortic and the pulmonary artery valves, where you hear that murmur in relationship to those sounds will tell you a lot about the murmur and what it might be. So we have 3 choices up here. We have mitral stenosis. Think about when you would hear a stenotic valve in the cardiac cycle, when you would hear a stenotic mitral valve. Aortic insufficiency, when would you hear an insufficient aortic valve? And mitral insufficiency, when would you hear an insufficient mitral valve? This is a tough question right now. It won't be tough before the midterm, you'll know. But just for the heck of it, who says mitral stenosis? Outstanding. Okay, who says aortic insufficiency? Outstanding. Great. Who says mitral insufficiency? All right, outstanding. Okay, the majority of you guys got it right. But I appreciate the rest of you guys sticking your neck out and making a choice. That helps me a great deal, and it says good things about you. Go ahead. You sure will. Just a sec. Good point, though. You don't think I was just going to leave you hanging, do you? This should look vaguely familiar to you guys now. We did it last lecture. This is the Wiggers diagram. It represents basically what's going on in terms of pressures and volumes over one cardiac cycle, okay? You will note that the semilunar valves open here, close here, and the AV valves open here and close here. This is S1, this is S2. You are hearing the murmur in here, okay? Now, an insufficient valve is a leaky valve. You hear the murmur when that valve is closed. Stenotic valve is a narrow valve. You're forcing a whole bunch of blood through a narrow opening. You hear that murmur when that valve is open. So let's talk about mitral stenosis. When is the mitral valve open? It opens here, right after S1, or right at S2, excuse me, remains open here, and then closes here. What phase of the cardiac cycle is that, systole or diastole? Those of you who can't read. Diastole, thank you. So she's got a systolic murmur. So is it likely to be mitral stenosis? No. Okay. If you think about the cardiac cycle, think about where you're hearing the murmur relative to the other sounds, that gives you a clue as to what it might be, and that ain't what it is. Okay. We talked about aortic insufficiency. Here's where the aortic valve closes, and here's where it opens. What period is that? Those of you who can't read. Diastole, thank you. So, which one is it? It is mitral insufficiency. The mitral valve closes here, right at the beginning of systole, and it opens here, admittedly, somewhat toward the end of ventricular systole, but when you're listening to sounds, you know, you can't put, you can't just draw a line and say, okay, you know, that's where systole ends, and I'm still hearing the sound. You might hear it a little bit into diastole, you still call that a holosystolic murmur. You heard it all the way through systole. Mitral insufficiency. The pressure in the ventricle is going up. The mitral valve closes because the pressure in front of the valve exceeds the pressure behind the valve. Blood wants to flow from the ventricle to the atrium. Your valve is stopping that. It wants to flow from high pressure to low pressure. You put a valve in there to make sure that doesn't happen. The pressure increases, and eventually it exceeds the aortic pressure, and the aortic valve opens. The pressure behind the valve exceeds the pressure in front of the valve. You want blood to flow from the ventricle to the aorta. You want it to flow down its pressure gradient in that case. The valve is open. Okay. You would hear a stenotic aortic valve during systole as well. Okay. We'll talk about that during the cardiac cycle workshop. That's a little preview. Okay. So let's talk about what's causing that increase in pressure. We're talking about cardiac cell contraction, right? This is the contractile response here in terms of tension generated. This is your cardiac action potential. This is the ventricular action potential, unless otherwise specified. When we say the cardiac action potential, that is what we're talking about usually. Okay? So you will note that the action potential duration is roughly the same duration as the contractile response. I realize this figure is different from what's in your notes. What's in your notes is out of Byrne and Levy. We have permission to put that figure in your notes, and that's why it's there. It does not demonstrate that nearly as well. That's why I'm using this figure right now. I think the one in your notes is an isolated cardiac myocyte. There is no tension on it, and that's the reason why it's delayed there. So you can kind of ignore that. It's nevertheless, you'll note the contractile response, roughly the same duration as the contraction, okay? So why is, shoot, doggone it, why is that action potential duration longer? What's going on here that is not going on in a skeletal muscle action potential? Remember, skeletal muscle, it's contractile tissue. You know, muscle contracts in response to increases in calcium in skeletal muscle. Why is this different? Why is cardiac muscle different? Why would the action potential be different from skeletal muscle where you've only got like a 2 millisecond action potential? What do you think? Okay, well, I'll tell you why. Now you'll know. We have calcium channels in the cardiac cell membrane. Okay, and they're very active. There are a lot of them, and calcium is necessary for cardiac contraction. That is, calcium has to cross that membrane in order for contraction to take place. That generates a significant current. Okay, calcium coming in, positive charge coming in to the cell, tends to make voltage go up. Okay, so what's happening here is we have positive charge coming in the form of calcium that would not be coming in skeletal muscle, where the calcium currents aren't very fast and they're weak, and they aren't necessary for contraction. Okay? Calcium comes in, that has an effect on voltage. We have different channels in the cardiac myocyte, that affects the shape. That's affecting the shape here, it's making the duration longer because calcium influx is coming in and holding that voltage up. Okay? Remember that sodium channels are gated by voltage, so are calcium channels. They have an activation gate and an inactivation gate, okay? And calcium flows into the cell, down its concentration gradient, increasing cytosolic calcium concentration and causing contraction. It's not the whole story, but that's a good part of it. And that increase in calcium, that's a current coming in, positive charge coming in, makes your voltage hang up, okay? That's why we have a different action potential. Different channels. And I did note that, but you will note it as well. The figure in your notes does not demonstrate that as well. So the calcium's coming in. Let's take a look at the structures in our cardiac cell. These should look very familiar to those of you who remember skeletal muscle. They do act differently. Okay? We do have a sarcoplasmic reticulum. That would be the endoplasmic reticulum in other cells. It is the storage molecule for calcium. Okay? It's an intracellular organelle, and the calcium is stored because it is taken up into the SR via an SR calcium pump, just like skeletal muscle. We have a calcium ATPase that brings calcium in and stores the calcium. And there is a release channel, again, very similar to skeletal muscle. It is a ryanodine receptor. Okay? So this should all be very familiar to you guys. We have transverse tubules. How about that? Same thing in skeletal muscle. That is meant to bring your extracellular space and your action potential down into the cell. Okay? Remember, we talked about the fact that you have, well, now we're talking about it. You have calcium coming into this cell. It's a fairly large cell. It's a little bit, it's like skeletal muscle in that case. It's not quite as long. The cell is only about 100 microns long. And it's about 20 microns thick. Well, 20 microns doesn't sound like a whole lot, but biologically, that's a mile. Okay? It's going to take calcium a long time to diffuse 20 microns into the center of a cell to cause contraction. So what you do is, if you're Mother Nature, If the calcium's too far away, you design something to bring the calcium closer, and that's what the T-tubules do. They dip into the cell. What's in the T-tubule is effectively extracellular space, lots and lots of calcium. You bring calcium into the inside of the cell so that you don't have to wait a few seconds for it to diffuse 20 microns to get to the middle and cause contraction. That would be a problem. Now you bring it in and it doesn't have to diffuse nearly as far. Diffusion, a wonderful form of transport, but the distances have to be short. You guys know that. Okay. So the action potential dips into these T-tubules just like it does in skeletal muscle. Calcium comes in through the membrane. It comes into a junctional cleft just like it does in skeletal muscle. And different from skeletal muscle, it causes something called calcium-induced calcium release. Skeletal muscle has the voltage sensor in the membrane directly hooked up to the ryanodine receptor, and when the voltage sensor changes conformation, the ryanodine receptor changes conformation because they're bound together, and you get release. In this case, the two proteins are separate. They are not connected. And calcium comes in through the calcium channel, in this case, and it binds to the ryanodine receptor, and that opens the ryanodine receptor and you release calcium. So for skeletal muscle, you don't need calcium influx for contraction to take place. For cardiac muscle, you do. It is an absolute requirement, okay? So it's a different mechanism than it is in skeletal muscle. And then you get calcium-induced calcium release, and roughly 2/3 to 3/4 of the calcium that is needed for contraction of a cardiac myocyte does come from the SR. The other quarter comes across the SL membrane and causes contraction, okay? So you will note that this is not just trivia. Decreased SR calcium causes decreased release in heart failure, and that would be one reason why you would have a negative inotropic state in heart failure, okay? It's one of many, but it is one, okay? You do get decreased SR calcium release. That means decreased calcium. That means decreased contraction, okay? And it is largely because how the SR calcium determines how your heart is going to contract. That's different from skeletal muscle where it's virtually all or none. You open them up and the calcium flows out and you get contraction of myofilament. This is much more graded, okay? And by being graded, that means you can alter it. You can make more release happen and get better contraction in a cardiac cell, okay? We'll talk about that ad nauseum. So calcium causes contraction. This will also look very familiar to you. You have tropomyosin sitting in that groove in actin, covering up the myosin binding sites. You have actin there. We have troponins, troponin T, I, and C. These move the actin out of the way in response to an increase in calcium. The calcium binds to troponin C. And that is altered in cardiac myocytes. We'll talk about that. It's a regulatory mechanism, okay? And of course, we do have the myosin there, and the myosin head binds to the actin when that tropomyosin is moved out of the way. You guys, very similar to skeletal muscle, okay? That myosin forms myofibrils, very similar to skeletal muscle, okay? So we have bundles of actin and myosin, and you will note that those are not the only proteins that are relevant to contraction in cardiac cells or in skeletal muscle. Again, I will bring up dystrophin. I know you've heard it at least twice, but it's a nice example of what can happen when physiology goes wrong. Dystrophin is the dystrophin complex connects the actin fibers, the contractile fibers in your cell, or the structural fibers, to the extracellular matrix. And that's fairly important because it means when you get contraction of a cardiac cell or a skeletal muscle cell, it will drag the extracellular matrix and therefore the rest of the tissue with it. And so the dystrophin complex bears the force, okay? If there's a mutation in that complex and it's disrupted, then the membrane bears the force. And when your cell contracts, the membrane is expected to drag the extracellular matrix and the rest of the tissue with it. And that doesn't work real well. Membranes are the little floppy things made of lipid. They tend to tear when you put a lot of tension on them. And at least in theory, that's what the majority of the field thinks, that's exactly what happens. You get tears in the membrane because all of a sudden this complex isn't there to drag this extracellular matrix and the rest of the tissue along with the cell when it contracts. And so the membrane bears the force, it tears, it allows calcium in, the cells die, and bad things happen, okay? Right now, that's what the majority of the field thinks, okay? All right, for what it's worth. Okay. That might be the last time you hear about dystrophin, so you can take a deep breath and relax, at least from the M1 perspective. Higher calcium concentration achieved in the myoplasm during the action potential. The more calcium you have, the more force you generate. And usually what positive inotropic drugs do is they increase the amount of calcium release or the amount of calcium influx across the sarcolemma to cause more calcium to accumulate in the cytosol and cause more contraction, okay? So you get a more forceful contraction and therefore a bigger stroke volume, bigger cardiac output, more perfusion of the tissues, okay? Calcium influx ends when the action potential terminates and the SR calcium release terminates. And that is the point at which you start to get uptake into the SR via the SR calcium pump, the SR calcium ATPase, and you get calcium efflux across the sarcolemma back out into the extracellular space, largely via the auspices of the sodium calcium exchanger, okay? Because what comes in has to go out. If calcium's coming in across that sarcolemma, lengthening your action potential, then it has to go back out again, and it goes out mostly through the exchanger, okay? So contraction ends as cytosolic calcium falls. So that was contraction of the cardiac myocyte in a nutshell. So let's talk a little bit about our video. Once again, this is an echocardiogram. And you will note, this is dilated cardiomyopathy. This wall should be moving in, like into here, right? And it ain't moving in. That's because there's a problem with the contraction of these myocytes. She's in a negative inotropic state. There are a number of reasons for that, but one of them is the fact that her myocytes are diseased. They don't contract as well, okay? So you will note this is something that comes up clinically. And it happens a lot. That process gets messed up. When it gets messed up, it's not just a problem on the level of the L-type calcium channel or the ryanodine receptor. It's a problem you see in an organ, in a patient, that results in symptoms, okay? So note, once again, I mean, the primary reason for bringing it up, we're not down here wasting your time talking about proteins, okay? You go up and down the scale. The effect on one goes up, and it results in things that you see clinically. This is all really relevant, okay? I'm sure that when you had a lot of this in biochemistry, it did not seem so. That's because we hadn't gotten here yet. But it is, I assure you. All right, let's talk more. So the way that your heart works is actually controlled. And it's controlled by largely through the auspices of the autonomic nervous system, okay? We're going to talk a lot about the autonomic nervous system in this block. Dr. Cohen's going to introduce it. He's going to introduce it in all the organ systems, but it's introduced in this block because it has the biggest implications, in my opinion, for the cardiovascular system. The autonomic nervous system is split into two branches, the parasympathetic and the sympathetic branch, and they usually do opposite things, okay? In the case of the heart, the parasympathetic branch of the autonomic nervous system innervates the SA node, the AV node, and the atria. And it does that via the auspices of the vagus nerve, okay, which is one of the cranial nerves that you'll be learning about if you haven't learned about already. I think they're going to bring that into this block. As a matter of fact, I'm positive of it. The sympathetic nervous system innervates the SA node, the AV node, and the atria, and the ventricles, okay? Anatomists will tell you that there are parasympathetic nerves in the ventricle. Physiologists will tell you that it doesn't matter because they have no effect. So for the purposes of this class, for what I'm telling you, they might as well not be there, okay? The parasympathetic nervous system affects the atria, the SA node, the AV node. The sympathetic affects all three of those plus the ventricle, okay? So you will note that the sympathetic nervous system, you get release of norepinephrine at nerve endings. That's NE. You also get epinephrine release from the adrenal glands as a part of that, okay? This ends up in the circulation and sort of circulates throughout the body. This is much more local. It's released right onto the tissue, okay? A little bit more of a more controlled response. These molecules bind to beta adrenergic receptors. It is mostly beta 1 in the heart. The beta 2 don't have much effect in the normal heart. They are upregulated in cardiac in heart failure. Nobody knows why, but there may come a point in your career when somebody will come up with a drug that alters binding at beta 2 receptors. They're upregulated in failure. That would be why. But in the normal heart, mostly beta 1. Okay. All right. What's next? Come on. There we go. ACH is released at the nerve endings of the parasympathetic nerves. This should be familiar to you from skeletal muscle. It is the same ACH that is released in synapses, like the neuromuscular junction, okay? However, note that ACH binds nicotinic receptors. The ACH that's released in the parasympathetic nervous system binds muscarinic receptors, M2 receptors, okay? Different receptors, these don't react, guess what, to nicotine, okay? So they're a little bit different, but the acetylcholine's the same, okay? All right, and those are G-coupled, protein-coupled receptors. I know you've heard a lot about that in CMB. They don't usually hook it up too much to physiological responses. It's not a physiology block. We're going to do that here. So the sympathetic nervous system, when you get release of norepinephrine from sympathetic nerve endings, you get a positive chronotropic effect, increased heart rate. Okay? Increased heart rate, increased cardiac output, increased blood pressure, increased perfusion. Okay? You get a positive inotropic effect in the atria and the ventricles. That is, your cardiac cells contract harder. There's more calcium release, okay? And that results in a higher stroke volume, higher cardiac output, higher blood pressure, more tissue perfusion. You get a shortened AV nodal delay. So I took you very quickly through how the action potential propagates throughout the heart. We start at the SA node. We propagate into the atria. And the atria become depolarized and they begin to contract. And then remember, the AV node is the only point of electrical communication between the atria and the ventricles, okay? Well, it's a little more significant than that. The action potential propagates through that AV node very slowly, and it creates a delay, a noticeable time delay, a measurable time delay. That time delay is there to allow the atria to contract and allow them to eject that extra bit of blood into the ventricle before the ventricles begin to contract. So you delay, get your atrial contraction, get the blood in, then the ventricles depolarize and they contract. Okay, what norepinephrine does is it shortens the AV nodal delay. It increases the conduction velocity of the action potential through the AV node. We'll talk in detail about how that happens. You increase the SR calcium pump activity. Okay. Kind of puzzling, isn't it? Why would I want to increase pump activity? Wouldn't that decrease calcium in the cytosol? Why do you think? Anybody want to stick your neck out? How much time is there in between beats if I increase the heart rate? Less or more? A lot less, in some cases, depending on how much it goes up. So as your heart rate goes up, you have to get rid of that calcium faster to get ready for the next beat. And you have to get it stored in the SR to get it ready for the next beat. And the more you store, the higher the calcium will be on the next beat. So increasing the pump activity, A, increases the force on the next beat. B, gets that calcium out of there so that your heart can relax and get ready for the next beat, because that has to happen quicker when you increase the heart rate. Altered gating of the SR calcium release channel, don't worry about that excessively. It's still a developing field, but most people do believe that the release channel is more likely to open when you get adrenergic stimulation, and that can increase SR calcium release. Decreased myofilament calcium sensitivity, once again, counterproductive. What the heck? Aren't we supposed to be increasing contraction? Why would we want to decrease the myofilament calcium sensitivity? We've increased the heart rate. And that means that we not only have to contract more, we have to relax faster, okay? You have to get that heart relaxed. You have to get filling to take place quickly in order to get ready for the next beat when you have a higher heart rate. So this is counterintuitive, okay? But it is true. Myofilament calcium sensitivity goes down in adrenergic stimulation, and you get an increase in the force of contraction despite that, because the calcium goes up so much. And the reason it goes down is to allow you to relax faster. It's all about getting ready for the next beat, okay? You can't just increase the positive side. You have to increase the rate at which the relaxation takes place, or it won't work. Shortens the action potential duration, same thing. The action potential has to terminate faster to get ready for the next beat, okay? It seems counterintuitive, but nevertheless, you should know it, and you will. Shortened contraction duration, that's a result of all that stuff, okay? Once again, get ready for the next beat. So here's how it all works. A lot of this will look familiar to you, but I know you had it some months ago. Norepinephrine binds to the beta-1 adrenergic receptor, just like any ligand binds to any general receptor, just as you learned it in CMB. That activates G proteins, just like you learned it in CMB. In this case, it's GS. The G proteins activate adenyl cyclase. ATP is converted to cyclic AMP, which is a second messenger, and I know you had that from Dr. Levin. Cyclic AMP binds to protein kinase A and activates it. I know you had that from Dr. Levin. It may have been quite a long time ago, but you had it. However, we are not going to stop where Dr. Levin probably stopped. We're going to talk about what that pKa does now. It phosphorylates channels and other proteins throughout the cell in an effort to cause those adrenergic responses, the sympathetic responses that I went through a moment ago. And let's go through them again. Don't forget that cyclic AMP is broken down by phosphodiesterase, and that will terminate your sympathetic response or help keep it under control. We have a positive chronotropic effect. That happens at the SA node. Here's my SA nodal action potential. Remember, I said the faster this potential here in phase 4 rises, the quicker you get to threshold, and the faster you get an action potential, the higher the heart rate. This channel is your pacemaker channel. We'll talk a lot more about it later. That increases this slope, okay? Increased activity of this channel increases that slope, okay? That is a result of this second messenger cascade. The calcium channel is activated. This upstroke is carried by calcium in the SA node, not sodium. And remember, we talked about more sodium channels, the lower the threshold potential. Well, in this case, it's more calcium channels, the lower the threshold potential. So now, not only are we increasing our slope here and getting to threshold faster, we've actually lowered the threshold potential by activating calcium channels, okay? That's how it works. Quick round the horn, believe me, we'll go through it again, okay? We decrease the conduction velocity, or increase the conduction velocity, in the AV node. More sodium channels, higher action potential conduction, right? The same thing works in the SA node and the AV node where calcium carries the upstroke. The AV node is very similar to the SA node in that respect. These are calcium channels carrying the upstroke in the AV node. Activate calcium channels, higher action potential conduction velocity, just like in nerves, only it's calcium channels here, not sodium channels, okay? Inotropic effect. In the ventricle and in the atrium, this would be due to increased calcium channel activity, L-type calcium channel activity, all right? Bring in more calcium, that gives you more calcium for contraction. In addition, the more calcium you bring in, the more calcium-induced calcium release you get, and the more calcium you get released from the SR. Okay? So it actually has an effect on both. Shortened action potential due to the increased activity of K channels, specifically the delayed rectifiers. We'll talk in depth about this. But more potassium efflux means you're dragging your voltage down toward rest. You need more potassium efflux in order to shorten the action potential and get to rest quicker. Okay? That's what's happening here, and that's why the K channels are activated, specifically the delayed rectifiers. Of course you can.
It makes sense that if calcium was being pumped out more quickly, that would allow for the action potential to be quicker and for the cell to recover and to have another one.
Mm-hmm.
But I'm a little confused why pumping calcium into the cell faster, more efficient.
It's not into the cell, it's into the sarcoplasmic reticulum. And so what happens is calcium is stored in the sarcoplasmic reticulum for the next beat. It's high in there, and the higher it is, the more calcium release you get, because you get a bigger gradient, if nothing else. There's more to it than that, but we don't have to worry about it. You get a bigger gradient for calcium. When I open up those channels, the calcium goes out faster, okay? So the more calcium I accumulate in the previous beat, the more release I get in the next beat, okay? Make sense?
Yeah.
Great. And how fortuitous. We've brought it up right here. Yes, I know, astounding. There we are, increased calcium removal, increased calcium pump activity, okay? Reduction of relaxation time, that's because we've increased our pump activity and because we've reduced the myofilament calcium sensitivity. Seems counterproductive, it is not counterproductive. It allows you to relax faster, okay? Or not entirely counterproductive. Okay. How about the muscarinic side? It's going to look very familiar and a little bit simpler. We have a decreased heart rate, okay? And that is due to activation of another K channel. This one's different, okay? It's in the SA node. And that K channel drags you down toward EK, minus 95. So the more potassium channel activity I have at rest, the more I'm being dragged down, and the less quickly that resting potential, that phase 4, rises and hits threshold. It drags that voltage down, keeps it from rising quickly. Decreased action potential, conduction velocity, okay? On the muscarinic side, ACH binding to M2 receptors. Note, it has a negative effect on adenyl cyclase, less cyclic AMP, less pKa. If I have more pKa activity, I increase AP conduction velocity. If I have less, I decrease AP conduction velocity. And that's another reason why your heart rate decreases as well. Decrease cyclic AMP, you decrease all those effects we just talked about on the sympathetic side. And you get a decrease in heart rate, not an increase. Decreased force of contraction of the atria, not the ventricle, okay? Negative inotropic effect. ACH, M2 receptor, G protein, this is a GI, this is an inhibitory protein. It inhibits adenylate cyclase, decreases cyclic AMP, increases this different potassium channel in the SA node, and therefore decreases heart rate, okay? As well as reversing all those other effects on the sympathetic side. So here's the whole picture. And the reason I'm showing you the whole picture, number one, these have opposite effects on cyclic AMP and on a lot of the aspects of cardiac contraction. I also have the word tone in bold caps. That is because you guys are like most people, probably like I used to be a long time ago, way too long ago, in that you probably think about these systems as a light switch. You flip the switch on, high sympathetic activity, and you flip the switch off, low sympathetic activity. And that ain't the way it works. The sympathetic system and the parasympathetic system have what we call tone. What that means is that they're active all the time. Both of them are active all the time. And it's a question of whether you increase them or decrease them, and the balance between the two that determines what effects you see in the cell. So don't think of them as light switches. Think of them as those light dimmers that you have, like I have in my kitchen, where I turn the dial and the light comes up, and I turn it back and the light goes down. These are dials, okay? And I can dial up the sympathetic and dial down the sympathetic and predominantly get sympathetic effects, or I can dial down the sympathetic and dial up the parasympathetic and get predominantly parasympathetic effects, but they are active all the time. There's some volume there on both sides all the time, okay? And it's a question of where the balance of the two comes out, okay? It's a fairly important concept. You can't get away with thinking of them as light switches. It won't work here, okay? Hopefully that will be emphasized during the course of the block. Let's talk a little bit about the inotropic drugs. And let's start with the cardiac glycosides just a little bit. You're going to hear more about this later. It won't be the last time you hear this, but I want to take you through it quick as a preview and also to give you an idea of what we're talking about in this block and why I keep going up and down the stairs, okay? These are sodium-potassium ATPase inhibitors, and figuring out how they work requires you to make jumps in logic. They make great application questions on exams, okay? If I decrease the sodium-potassium ATPase activity, what will happen to the intracellular sodium? Usually it's pumping sodium out, so the intracellular sodium will go up, and I'll have less of a gradient for sodium across my membrane, okay? Like so. If I have less sodium gradient, what happens to the sodium-calcium exchanger activity, our secondary active transport? Goes down. The sodium-calcium exchanger is using that sodium gradient to pump calcium out of the cell. If I decrease the gradient, I get decreased calcium pumping activity and less sodium-calcium exchange activity. If I get less sodium-calcium exchange activity, what happens to the calcium in the cell? Up or down? Up. Up, because I'm transporting less calcium out of the cytosol. I've got more calcium there. Now, here's the tricky part. Decreased calcium removal, increased cytosolic calcium during diastole. Now, if I have increased cytosolic calcium during diastole, what does that do to my SR calcium pump? I have an SR calcium pump. It's like any other enzyme in your body. There's a substrate and a product. The substrate is cytosolic calcium. The product is SR calcium. If I increase the substrate, what happens to the activity of my enzyme? The conversion of substrate to product goes up. And I get more calcium accumulation in the SR. If I get more calcium accumulation in the SR, my SR calcium release goes up. I've increased the calcium gradient. And I get increased release. And that results in even more cytosolic calcium during systole. And that results in more force of contraction. And that results in a higher stroke volume. And that results in higher cardiac output. And that results in higher blood pressure. And that results in better tissue perfusion. And that results in a better patient. Okay? Lots and lots of steps. Sorry about that. I think you can see this is how it works. Okay, sorry. It's my job to teach it. I didn't design the system. That's just the way it is. And that's why our exams are the way they are. Okay? Let's talk about the other inotropic drugs. This is a little bit better. This is sympathomimetics. They mimic sympathetic neurotransmitters like norepinephrine, epinephrine, dopamine, dobutamine. These all stimulate beta-1 receptors. So they're all going to cause the same effects that beta-1 receptors have. One thing to note, they don't just bind beta-1 receptors. They also bind beta-2s, which, and I said there weren't many beta-2s in the heart. There are numerous beta-2s in vascular smooth muscle. They cause dilation. You'll get to that. And there are alpha receptors that cause vasoconstriction. These drugs all have different affinities for all these receptors. What affinity they have for these receptors determines what side effects you're going to see. So it's all well and good to stimulate beta receptors and get a positive inotropic response, but don't forget, they're probably, almost certainly not going to just bind beta receptors. They're going to bind adrenergic receptors of different types all over the body and cause side effects, which is why Dr. Cohen is going to stand up here and bore you with the adrenergic system next week or the week after, okay? And it's going to seem like trivia, and you're going to have to memorize where all these receptors are and what their effects are. Sorry about that. It's irrelevant. Sorry. Okay. The phosphodiesterase drugs, amrinone, milrinone, phosphodiesterase inhibitors, inhibit this enzyme, which breaks down cyclic AMP and gets rid of this pKa effect. So if I inhibit phosphodiesterase, I will actually increase cyclic AMP, I will increase active pKa, I will increase all this, okay? So that's how that drug works. A little bit different. We talk a lot about second messenger systems, and I'm sure you were bored with them in cellular and molecular. I don't blame you, but it's relevant. Sorry, this is where the drug works, okay? And you have to know the second messenger system if you're going to understand how it works, okay? So, inotropic drugs illustrate the effects that you can get by altering the activity of one protein or a group of proteins and causing huge effects in terms of what you see in a patient or in a human being in terms of what you just see when they walk in, okay? This is how drugs work. In the case of the inotropic drugs, generally speaking, we get increased calcium entry, for instance, through the L-type calcium channels or something like that. Higher myoplasmic calcium levels. Higher calcium increases the force of contraction. Higher force of contraction increases stroke volume. Cardiac output, stroke volume times heart rate. Most of the time, the heart rate goes up too. If they go up, cardiac output goes up. If cardiac output goes up, arterial pressure goes up. If arterial pressure goes up, you'll increase the perfusion of your tissues. That's how the drugs work. Generally speaking, that's how they work. Don't forget, they have side effects, and these are relevant to what we're going to talk about too. If you play with the sodium gradient, unfortunately, the sodium-calcium exchanger is not the only secondary active transporter in the body that uses sodium. There are a lot of them, and there's sodium-potassium pumps all over the place. They're in the basement membranes of almost all those epithelia that we talked about way back when, okay? Decreased sodium gradient is going to decrease or change the transport of a lot of substances, and you're going to get side effects. You'll get side effects from inhibiting the exchanger if they overdose on the drug, okay? So you can't just remember the positive, you have to remember the negative. Remember the sympathomimetics, the phosphodiesterase inhibitors. They're going to increase heart rate. They're going to have effects all over the body that we're going to talk about a little bit. This can cause arrhythmias. It can cause hypertension, okay? We're going to talk a little bit about that and how that works. For the next lecture, I don't know, you'll have finished, I think, Lloyd Carthen. I think that closes Monday, right? So think about Lloyd Carthen. He's been given metoprolol. That thing. That's a beta blocker. Generally speaking, this medication will produce increased cardiac output, no change in cardiac output, or decreased cardiac output. Think about it. Think about it in the context of the case. Think about whether it makes sense. And we'll talk about it at the beginning of the next lecture, and then we'll talk about why you would give a beta blocker to a patient. A little bit, all right? Finishing on time, I'm so proud. I'll see some of you guys this morning, the rest of you Monday.